In this lesson we're going to look at energy transfer in electric circuits, and we're going to take this simple circuit here as an example. And the question we want to ask ourselves really is how much energy is going to be transferred to this resistor in a certain period of time t. Okay, now we remember that when we close the circuit, an EMF from the cell pushes a current around the circuit through the resistor. And so this is represented here by this diagram, which shows coulombs of charge being pushed around the circuit. And as each coulomb passes through the resistor, it transfers energy to that resistor. So we can say that the energy transferred to the resistor in time t, seconds, is equal to the energy transferred by each coulomb as it passes through the resistance. That's the energy per unit charge multiplied by the total amount of charge that passes through the resistance. Let's restate that in terms of units just to help you see this. What we're saying is that the energy transferred over a period of time by this through this resistance is equal to the number of joules transferred by each coulomb as it passes through the resistor. That's the joules per coulomb, multiplied by the number of coulombs that pass through the resistance. Okay. Now in the previous lesson we learned that the energy transferred by each coulomb as it passes through this resistance is equal to the voltage across the resistance. Let's say we say the voltage is equal to the energy transferred per unit charge. And we also learned that the current flowing around the circuit, I, is equal to the amount of charge that passes every second. That's Q divided by T. And so the total charge that flows through this resistance, Q, just rearranging that equation, is equal to I, that's the current flowing, multiplied by the period of time T. So we can say that if the current flowing around the circuit and through this particular resistor is I, and the voltage across the resistor is V, then the energy transferred to the resistor is equal to, here, E divided by Q, which is V, multiplied by the total charge, which is Q is equal to I times T. In other words, the energy transferred is simply the voltage across the resistor multiplied by the current flowing through it during that period of time t in seconds. Now we also remember that the power P being transformed in this resistance is equal to the energy transferred per unit time. Let's say the number of joules which have been transformed per second. Well, that's equal to, using this equation, V times I times T divided by T, which is equal to V times I. So the power transformed by the resistance is simply equal to the voltage across the resistance multiplied by the current flowing through it. A nice simple formula. Okay, let's just consider a simple problem. Supposing that we've got the circuit like this and we measure that the current flowing through the circuit, I, is equal to 3 amps. And then we measure the electrical potential difference across the resistance, and we find that the voltage V is equal to 20 volts. And we want to calculate how much energy is transformed, say, in 1 minute. Well, as we've just seen, we can say that the energy is equal to the voltage multiplied by the current multiplied by the time in seconds. So that would be 20 volts multiplied by 3 amps multiplied by 60 seconds, which would be 3,600 joules. Okay, if we want to work out the power consumed by the resistance, that's to say the rate at which energy is being transferred or transformed by this resistor, well, the power is equal to energy divided by time, which is equal to V times I, which is equal to 20 times 3, which is equal to 60 joules per second, or 60 watts.